Example 4. Fluid mechanics. Chapter 5. A prototype airplane with a chord length of prototype 1.6 meter is to fly at Mach number NA equal to from 2 at the altitude of 10 km standard altitude. A 1/8 scale. So we have a 1/8 scale of the prototype is to be tested in a helium wide tunnel at so for the fluid helium and at 180 atmosphere pressure. Find the helium test section velocity that will match. So find helium test section velocity V, in this case Vm for the model, because the helium is a model and prototype is air. Will match the Mach number and Reynolds number of the prototype. In each case, criticize the lack of dynamic similarity. What high pressure in the helium tunnel will be match both the Mach and the Reynolds number. And the pressure of the helium model at and prototype. Mach and Reynolds numbers. What does part C still not active dynamic similarity? So at first we are going to calculate the dimensional less parameters for prototype and model. In this case, consider for the helium R equals to from tables S to K, K equals to the which is Cp on Cv and the viscosity of helium is approximately 2 gram on the meter second. From the prototype law, and n equals to the relation from the power law. Calculate the helium speed of sound and velocity. For the helium sound velocity, we have this relation called RT, which is we have the car is R multiplied to the temperature, which is 100 Celsius and 377 Kelvin. We can obtain for the Mach number, for the Mach air equals to this is for prototype, and for helium model. To obtain the velocity of the model Vm, which was on our unknowns, we have the Mach number for the problem, which was 2 at 10 kilometers altitude from our now. We can make an equality with Vm, which is the helium, on the velocity of sound on the helium, which was calculated 1134. With the equality, we can obtain the velocity of the helium as the model fluid. If we write helium equals to the on second for a 1/8 model in the relation for equality of Mach number. For the equality of Reynolds number, we should first calculate the Reynolds number for model or prototype each of them. For this case, we should know the properties of the air at the meter altitude, which is available in the table A6 in the book. For the altitude of the, we have density for air equals to the and A air and new air from the power law. We have N isentropic for the air at the 10 km altitude. The air velocity can be obtained as V air Mach multiplied to A air. We have Mach 2. We can calculate V air equals to the net of second the model chord length is. For the Reynolds number, we should have made an equality of rho m, Pm, Lm on viscosity of model on the prototype Reynolds. In this case, for the prototype, we have Lp equal to the rho P, which is air obtained from table, mu P equals to and A equals to the, for model we have Lm 18 rho m obtained from table A4. We can calculate from the relation of the perfect gas. We have the pressure 1 atmosphere, which is Pascal, multiplied to the on the R, which obtained from table A4 before, and the temperature. So Pm, rho m calculated new, and we have a relation for the quantity before for um rho and Pm is unknown. With Mach and equality, we can calculate Pm. With Mach and equality, rho for equality of Reynolds, the Reynolds for air is at the 10 kilometer altitude according to the obtained data from tables. So should be equals to the prototype model Reynolds Vm, which is helium, and Vm equals to have a similarity in Reynolds number. This is the end of this example.